In this video, we're going to prove the intermediate value theorem. Basically, it says that if f of x is continuous on a closed interval, then for any k in between f of a and f of b, including the endpoints, there must exist at least one c in that closed interval ab such that f of this special c value actually equals k. And in the proof, there's a number of cases that need to be proven. Most of them we're not going to prove, believe it or not. Case number one. Suppose f of a is k or f of b is k. Then we simply choose c to be a in case f of a is k, or c is equal to b in case f of b is k. If they're both k, then you can choose c equals a or c equals b. Now, the next case, so that case is done. The next case is, suppose f of a is less than f of b, and that k is at least 0. Now, the other cases which I'm not going to show is f of a is less than f of b, and k is less than 0. And f of a is bigger than f of b, and k is greater than 0. Lastly, if f of a is greater than f of b, but k is less than 0. These last three cases, the proof of them pretty much follows from the proof of case number 2. Now, we are in case 1, we already dealt with f of a equaling k or f of b equaling k. So k is now strictly in between f of a and f of b. Then f of a is less than k, which is less than f of b. We don't have the equalities because we took care of them in case number 1. So what we have going on is the following. Let me just extend the page a bit. We have that either a little bit more than k or a little bit less than k. I want to find a c value such that f of c is k. So we're going to have, like I said, we're going to have to talk about a little bit more than k, a little bit less than k. Who wants to talk about more, greater than, or less than k? How about we convert this so we can talk about greater than, less than 0. So we are going to define a new function. We're going to define g of x to be f of x minus k. We bring down the function k units, so now we really want to find g of alpha that equals 0. G of c equals 0. Now note the following. Note, g of a, which is equal to f of a minus k, this is less than 0. Why? Because f of a is less than k. And then if you take away k, you're going to be negative. And g of b is equal to f of b, which is more than k. It says so right here. F of b is more than k. So when you take away k, you'll have something left over. That is your positive. So we want to find out when g of x is equal to 0. For example, if g of psi, which is f for psi, minus k is equal to 0, that would imply that f for psi equals k. When you subtract two quantities and the difference is 0, that's because the two quantities are equal. So it's okay to find out where g of x is equal to 0. So basically, what we want to do is find the following. So this is A, and this is B. Now we know that g of A is negative, and that g of B is positive. We like to find the first place where g crosses the x-axis, where g is 0. We want to find the first place. And then we're going to solve for that value. So I am going to define a function. I'm going to define x to equal the set of all little x's in the closed interval AB such that it has the following properties. For all y in the interval from A to an x, g of y is less than or equal to 0. Now, what kind of little x's in AB get to be in big X? Well, if this is the graph, and here's A, and it may come down again. B is somewhere to the right of that first 0. This point right here, that x, is in this set. Why? Because if you take any number between A and that x, g of that number, g of x, g of that number will be less than 0. For any value between A and x, g of those values are all negative. You could pick that value for x. Why? Because g of all of these values up to here, g of all of those values are less than or equal to 0. In fact, you can go, that's an x value. That's in capital X. Why? Because g of all of these numbers are less than or equal to 0. In fact, A is in capital X, because if you go from A to A, because X is going to be A, if you go from the closed interval A to A, which only includes A, the closed interval from A to A is just the set that contains A. And yes, it's true that all of those numbers, if you take g of them, you'll get less than or equal to 0. So we talked about what this capital X represents. Now, X is not the empty set, since I know of at least one element in it, 8. Because we know one thing for sure. G of A is less than 0. And X is in the set AB. Because we get the members of X only from that closed interval. It may be every element in the closed interval AB. It might just be a handful of them. But big X is in AB. So x is bounded, in particular from above. If x is non-empty and x is bounded, so let's write that. X not equal to the empty set and x bounded. That implies x has a least upper bound. We'll call it alpha. X has a least upper bound. And this is where the proof really starts. I claim g of alpha is 0. That is, this is our C value. The first place where it crosses. This is one of the C values. Happens to be the first place where g crosses the x-axis. Now, we have this obvious statement. G of alpha is less than 0. G of alpha is greater than 0. Or G of alpha is equal to 0. Well, if I show this isn't true, and I show that isn't true, I'm done. That must be true. And this is because G is continuous. So maybe at the beginning of the proof, I should say we're given that f of x is continuous on AB. And then I should say, so g of x, which is just f of x is continuous, y equal k, a horizontal line, that's continuous. So g of x is continuous on the interval AB. Okay, so now we have that. That tells us that g of alpha has to be one of them. The other alternative could have been that it didn't exist, but it's continuous. It has to exist. That is, g of alpha has to be something. Can't be undefined. Alright, so we're going to knock off the first two, this one and this one, and then conclude it must be 0. Suppose g of alpha is less than 0. Now, what's going on is the following. G of alpha is less than 0. And remember, it's the least upper bound. So, you have this. Then, since g of alpha is less than 0, alpha must be to the left of where it's 0. And I can put, let me move this over. I can put a neighborhood around alpha. We'll say that this left endpoint is alpha minus delta, and this right endpoint is alpha plus delta, such that we're going to pick delta small enough, such that f of this interval is always negative, which would give me that alpha plus delta, which is bigger than alpha, is in x. It'll be in x. Why? Because from a all the way up to a plus alpha plus delta, f of all of those values is less than or equal to 0. Oh, by definition, alpha plus delta is in x. But how can this be in x if that's smaller and it's the least upper bound? To be the least upper bound, to be an upper bound, you have to be bigger than or equal to every element in X. This is not an upper bound because it's not bigger than each and every element in X. So that's going to be our contradiction. Do I have nothing to write here? Good, I did. No space to write. Okay, so then there exists a positive delta such that for all xn alpha minus delta to alpha plus delta f of x is less than 0. Then for x in a, well, let me just say it this way. Then this, let's move it over. Then we have the following. Then x plus delta is an element of big X. Since alpha is greater than alpha, is less than alpha plus delta, alpha cannot equal the least upper bound of X. Because we found a larger element in X. Okay. So g of alpha is not less than 0. So now we're going to suppose the other possibility. Suppose g of alpha is bigger than 0. Now let's look at our diagram for this. If g of alpha is greater than 0, so here's the 0, and here is alpha. Well, once again, we can find a neighborhood around there, alpha minus delta up into alpha plus delta. Now, this here is an upper bound for X, because X only contains numbers from A up to that point. But this is larger. So alpha minus delta is an upper bound for X. But here's the contradiction. But alpha minus delta is less than delta. So delta, oh, I meant to say alpha, less than alpha. So alpha can't be the least upper bound of X. Why? Because I found the smaller upper bound. If anything, this alpha minus delta is a better candidate to be in the least upper bound than this. If you were to tell me, you know what, either that is the least upper bound or that is the least upper bound, and you told me that they were both upper bounds, you tell me that these are both upper bounds and that delta is positive, you better believe that I would pick this one to be the least upper bound. I'd be out of my mind to pick a larger upper bound for a candidate to be the least upper bound. Okay, so let's write that up. And let's see what we can do. So there exists a positive delta such that for all x in alpha minus delta to alpha plus delta, f of x is positive. And I do have one little error. These should be closed intervals. Okay. So, alpha not x. So, alpha minus delta is an upper bound for x. But alpha minus delta is less than alpha. So alpha cannot be the least upper bound of x. Why? I found the smaller upper bound. Okay, hence, the only reason we made a mistake, the only reason we found a contradiction to alpha being the least upper bound for x, because it is. Alpha is the least upper bound. Because every bounded closed set, every non-empty closed set has a least upper bound. Hence, what we suppose that g of x is less than alpha, well, it isn't true. Since g of alpha is not less than 0, and g of alpha is not greater than 0, then g of alpha is 0 for alpha in AB. Now, g of alpha is equal to f of alpha minus k, which equals 0. Oh, I'm real big on this one. If you subtract two quantities and the difference is 0, that implies that those two quantities are equal for alpha in AB. And that's all we wanted to find. We wanted to find an alpha in AB such that f of alpha or f of c is equal to k. And that would complete this proof. For homework, go and try to prove the other three cases. If you like this type of videos, please let me know. If you have any ideas of how to improve this video, or you think I made an error somewhere, please let me know via a comment. If you have a video that you would like for me to make up, hopefully the proof of some type of a theorem, let me know, and most probably I'll make up that video. So please get the point. Leave a comment. And as always, watch and learn.